So welcome to the quantum number lecture. So we left off with the Schrodinger equation. This was a physical equation of the atom that the conservatives, Schrodinger, Einstein, and others loved because it gave us a way to physically look at an atom, and at the same time, because of this function right here called the wave function, let the electrons exist as energy waves. These are actually standing waves that exist in a region of space we call orbitals. And we call them orbitals because we're giving Niels Bohr his due. Remember, he arranged electrons in circular orbits. Now, because of de Broglie's work and the work of G. Thomson and David Germer and Compton, we saw that electrons can and do act as waves. So this description in this beautiful equation describes the energy levels that electrons have based on them not existing in orbits but in orbitals. And these electrons are in a standing wave function that really represents their energy. And these electrons exist in this three-dimensional, we're going to see that a three-dimensional area, which is called an orbital, okay, arises from the solutions to this equation. Now, I am not at all versed enough through this equation to break that down for you. So I'm going to basically leap from this equation to three basic solutions, whole number solutions to this equation that describe the energy level, or where the electron as a wave of energy exists around a nucleus. Some of the same principles that Bohr had are still upheld. Electrons based upon proximity, if they're closer to the nucleus, are more stable and have lower energy. Electrons farther away. But there's more to it. So when I talk about the solutions to the wave equation, and there are actually three, I'm going to add one called magnetic spin from Linus Pauling. And what these solutions represent are numbers that describe the energy of every single electron. So what I'm trying to show you is that electrons exist in these orbitals, these wave functions. They're three-dimensionality. They have a three-dimensional structure to them, even though I may be showing you two-dimensional structures. And they do so, and they're based upon their energy levels. And we're going to know, and of course we know, that atoms are quantized. So these shapes have restrictions. So the four quantum numbers I'm talking about are four numbers that describe the energy level of each electron. That is, every electron requires a set of four numbers. That means that every electron has a unique energy level, okay, in an atom. And that's, of course, why Bohr could not describe any atom or ion with more than one electron, okay? So that's very important that you understand as we go through this. I'm describing the energy level of every atom with these four numbers. And these four numbers are going to give me a way to actually visualize where these electrons exist in proximity to the nucleus. Okay, so let's get started. Now, these four quantum numbers that we're going to talk about restrict each other, meaning as we go through the rules that describe these quantum numbers, that again will give us a picture of how the electrons are arranged based on energy in an atom, they restrict each other. So you can't have any possible quantum number. One quantum number's rules will restrict another, and that's because energy is quantized. So the first one, what we're going to talk about, is the principal quantum number, n. All right, and n is by far the most important one because it's the first one. And you need to understand that the index is size, meaning a larger principal quantum number means that that orbital, remember when I say orbital, the actual shape that electron exists in based upon probability, okay, that three-dimensional area of a standing wave of electron, okay, is bigger if this number is bigger. Okay, now I have S here, but don't worry about it. Now, this is really important because Bohr was able to find that electrons existed in orbits. Well, when n equals 1 in Bohr's orbit, okay, that shell that he used was smaller. So let me just write this down. So the first quantum number n starts us off. And this n is equal to principal energy level. So principal energy level. And it indexes It tells us something about the size of the orbital. So it indexes size. It's really important. And interesting enough, the Bohr atom, which of course is no longer, you had a positive nucleus, and of course you had these orbits or shells. And these shells got increasingly close together as we talked about. But the most important thing is the shell of electrons or these orbits that Bohr was discovering. Well, guess what? That is what n equals 1. So this one closest is n equals 1. Or I can do this. And this was n equals 2. So the shells of electrons that he found, okay, really paralleled the size of the first type of orbital, okay, that was in hydrogen. And we'll talk more about that. So Bohr was really on to more things that he recognized. So the circular orbits have something to do with size, and they matched up perfectly. Okay, in fact, there are 7 known sizes. So if the rule is n, very simply, okay, n is any integer. This is the rules for n. N is equal to any integer from 1 to infinity. Now, in truth, we know it goes up to 7. Okay, as a 4, 5, 6, 7. But in truth, it can go up to infinity. Okay, there's no limit. So this really represents, hey, the shells that Bohr was talking about. But instead of talking about in shells, because electrons don't go in orbits, we're talking about this is an orbital. It's important we go to the word orbital. Remember, that's a three-dimensional wave function or a three-dimensional area where electron exists as a wave, okay, and it has a particular shape. Now, the first shapes were circular, okay, and we'll talk about that in a second. But before we get going, let's continue on with principal energy level, because where we're going with these quantum numbers is to arrange electrons called electron configurations, and that's really going to tell a lot about the stability and reactivity of atoms. So going to the periodic table of elements, we can see magically it appearing. And you notice this period right here is 1, 2, 3, 4, 5, 6, 7. These are the rows in the periodic table. Now, this periodic table was built way before we understood what it all meant. There was something called periodic law that someone put this in order of atomic mass. It was changed by H. Moseley, put this in order of atomic number, but put elements in groups based upon their repeating reactivities. Now, the row in which it ends, notice there's 7. Well, that row represents your principal energy level. So being in the 5th principal energy level, guess what? You have elements that exist in this row. Now, there's the 2 other groups below here. You can't see the second one. We'll talk more about that. But that's important that you realize that. And being in the same group means you have similar reactivities. That didn't make any sense until we got to these configurations that we're going to get to through quantum numbers, through the Schrodinger equation. Now, party people, please stay with me here. So the n number indexes size. You guys know this. Going down a group, the atoms get bigger. Going across, you get smaller. Okay, we're going to learn exactly why. So rubidium is bigger than K. Why are the atoms bigger? Okay, well, there's a reasoning we'll get to, but the orbitals get bigger. The place or the region that they exist in as a standing wave are bigger as you go down. So the orbitals of rubidium are bigger than the same type of orbitals as potassium. Why? Because rubidium has an n equals 5. And why is fluorine smaller than chlorine? Because the orbitals by which electrons exist in, okay, are smaller for fluorine than chlorine, because guess what? Its n is smaller. Now we know that we get smaller going across because we increase the proton number, but we get bigger going across because we said already they have what? More shells of electrons. But those individual electron orbitals, not shells, are actually bigger. So n indexes size, and we can use that right here on the periodic table. All right, so we always start out with essentially how big are the orbitals. So when we do the notation for the atoms, we always start with one of the numbers, and we'll get to that. Now, that's the first one. Now, the second, okay, the second quantum number is this kind of script L. Sometimes it's called the azimuthal, sometimes it's called the angular momentum quantum number. Okay, and I'll tell you, angular momentum, you'll hear it, quantum number, or the azimuthal. I've heard it both ways when I learned this. It doesn't matter what really is this second quantum number, which, by the way, depends upon n. Remember, there's restrictions to each of these quantum numbers as we go through the rules. So what is the angular momentum number, or the azimuthal? Well, this, okay, is a type of number that actually describes the type of shape. And so we use this to figure out the actual basic shape of the place where the electron exists, called the orbital. So this defines the shape, the three-dimensional shape that electron exists as a standing wave. So it defines the shape. It's really important, the basic shape. And the way it does so is it defines a shape by understanding that this number, okay, really indexes preferred axes of the shape. Preferred axes. Let me explain what that means. Okay, how does it define the shape? Well, the number defines. For instance, if I have a L number azimuthal equals 0, what does this mean? Well, this means that I have 0 preferred axes. Okay, so the number defines how many preferred axes the shape has. So when this equals 0, you have 0 preferred axes, and you should know the shape with 0 preferred axes is a sphere. What's the preferred axes? Is it this way? Is it this way? I can draw, okay, segments in all directions. There's no preferred axes if you're a sphere. Okay, so anytime L equals 0 from the quantum numbers, then we know we're dealing with a circular orbital. Remember, an orbital is an exact place. So this is a circular or spherical orbital. And we call this orbital that's spherical an s orbital. Okay, now what is the restriction rules here? It's important we get that. We'll put that in green. Okay, the restriction rules, okay, is that L is equal to any number. So let's write it here. L is equal to, now it has to be based on n, 0 to n minus 1. What does that mean? Well, whatever n I'm in, okay, defines how many of these numbers. For instance, if n equals 1, if the principal energy level is 1, the first, quote, shell, we don't talk about shells anymore, equals 1, okay, then we put this in our law, and L is equal to what? 0 to n minus 1, and since n is 1, 1 minus 1, okay, of course, is 0. Now, what does that mean? So I only have a 0. So what's that mean? Well, that means very simply, I only have the 0, what? L number, or angular momentum number. So if I scroll this down, okay, and move this, I'm not sure why it moved, but hey, everyone's. So we move this down, okay, what do we got? Well, we got a 0. And if this quantum number, L, or angular momentum, equals 0, that means we have no preferred axis, and that equals an s orbital, which is a spherical orbital. Okay, so if you notice, when n equals 1, there's only what? One type of orbital. That's important. Let's go through these. Now let's pretend we have n equals 2. Okay, so let's say we have electrons that are in the second energy level, right? Okay, the second principal energy level, that'd be the second row in the periodic table, like for fluorine. So when n equals 2, what possible type of three-dimensional orbitals do we have? So we would go 0 to n minus 1, and we would have 2 minus 1, and that would give us 0 and a 1. 2 minus 1 is 1. So these are my possible numbers. And so if I have a 0 and if I have a 1, okay, then I have the s orbital, which is 0, and then I have a new orbital. Okay, now listen. So in n equals 2, I have the value of 0, which is an s orbital, but now I have another possible state of energy, okay, and that means L equals 1. Now I said that this is an s orbital, okay, 0, because it has what? 0 preferred axes. What would be the angular momentum for one preferred axis? Well, it's going to look like this. Okay, one preferred axis actually has a shape like a dumbbell. I don't know if you lift weights, but that's what we call a dumbbell shape. All right. And so this preferred axis is equal to 1 because if you notice, there's one direction, one axis that's preferred over another. And therefore, we call this the L equals 1 type of orbital. And it's got a letter name, okay, and we call it P. So when L equals 1, we have P orbitals. Okay, now it's very important you understand this. When L equals 0, we have an S. When L equals 1, we have a P. But the only time that you get an S and P type orbitals, okay, is when you're in the second what? Only in the second principal energy level are you allowed to have these two types, which means, this is important, you can have two S orbitals and two P orbitals. Now, what does that mean? Well, remember, the first number is the N number, okay? So when I talk about this S number, how is a 2S differ than a 1S? Don't forget, an S is circular. So if this is a 1S orbital that's circular, has 0 what? Has 0 preferred axes. A 2S orbital would be bigger and more importantly would encompass that one. So if I draw a 2S orbital, what it would do is not only exist outside that, it would kind of swallow it. So the 2s orbital, remember, a 1s orbital, electrons exist as a standing wave in this entire region. A 2s orbital, that's bigger because n is bigger, okay, would swallow this up. So electrons can exist in all that energy levels. All right, so it's important you realize that. So when we talk about the 1s orbital and 2s orbitals, you get confused. Remember that you have the 1s orbital. Remember, 1 index is size, s index is shape. Then we have a 2s orbital that's bigger, that fills that entire shape as well. And only when n equals 2, the second principal energy level, do you have these p orbitals that are dumbbell shaped. And this is a 2p orbital. It's very important. Now, it's important to realize because it's a 2p what orbital, and I didn't draw that very well, that 2p orbital is indexed by the size. So if I was to draw a 2s orbital that's bigger than the 1s, it's important to realize that 2p orbital should be about the same size. Oh, I can't draw it very well there. Let's go back. Okay, so let me just erase that. So that 2p orbital would be about the same size in terms of its length, okay, because it's 2p. All right, notice there's no p orbitals in the 1s. Why? Well, because there is what? No numbers that allow for it. Only when n equals 1 and you put in n equals 1 and for the rules for the what? 0 to n minus 1, okay, for the rules. Remember, L is equal to what? 0 to n minus 1. When n equals 1, you just get 0. So there are no p orbitals. And why? Because the atom is quantized. There's not enough of this orbital is not big enough to hold this energy level. Now, it's important to realize that as we get more complex, because there's two other shapes and they get more complex, not only are we talking about proximity, 2s electrons are farther away from the nucleus than 1s by statistics. And the 2p electrons are about a little bit farther on average because you notice we don't allow many electrons to move in this area. Their region of electron density or probability, radial probabilities, are farther away. But you can see it's about the same maximum distance that Bohr found. All right, very important. Okay, so 2s. Now what about 3s? Or the 3 principal energy level. So when n equals 3, what else do we have? Well, when n equals 3, okay, we have, let's do it. Put the n in this rule here for the L. This tells us the type of orbitals. What we got is 0 to n minus 1. Okay, now it's 2. So n minus 1 would give me 3 minus what? 3 minus 1 will give me a 2. But it's through all the numbers in between. So we get 0, 1, and 2. So when n equals 3, notice how many different orbitals. I have the L equals 0, which is the 3s. I'm just going to write 3s. We know that 3s is going to be a bigger circle than the 2s. We know the 1 is the 3p. and then the 2 is a new orbital, and it's called a D, a 3D orbital. Okay, and that has and now you say, well, what does that look like? Well, it's getting more complicated. One of the D's looks like a p orbital, but then it has a ring around it. Okay, kind of like a pacifier, and that's what we talked about earlier in the year. Okay, in crystal field splitting, and this, if you notice, will have two preferred axes. Okay, another example of a d orbital with two preferred axes is kind of like two dumbbells drawn like this. And if you notice, I know it's poorly drawn, but you have two preferred axes. So that's a D, and I'll show you those pictures. Now, can you guess what happens when n equals 4? Okay, if you following my drift here, when n equals 4, okay, what are the possible numbers? Well, of course, you're going to have 0 to n minus 1. You're going to have 0, 1, 2, and now 3. It's all the numbers 0 through n minus 1. So if you're in the fourth energy level, fourth principle, fourth row of the periodic table, n equals what? 4. Well, guess what? You're still going to have a 0, a 4s. Of course, it's bigger. It's still spherical than a 3s. You're going to have a what? A 4p. Same shape as a 3p, but bigger. You're going to have a 3d. I'm sorry, 4d, right? Because I'm in the fourth energy level, n equals 4. And then we're going to have one more. This n equals, L equals 3 is an f orbital. Okay, I'm not even going to try to draw them. They have, guess what? They have 3 preferred axes. And so I have the F, which starts, of course, in the fourth energy level. So I want to kind of review this to show you. So the first two quantum numbers really define what kind of shapes can exist in the individual levels. Please stay with me. So when n equals 1, what do we have? Okay, when n equals 1, let's put this into black here because I want to see it. N equals 1. That's the first row in the periodic table of the first major energy level. We only have an s orbital. When n equals 2, we have s orbitals and p orbitals. N equals 3, we have s orbitals, p orbitals, d orbitals. When n equals 4, we have s, p, d, and f orbitals possible. Notice something. As the n number increases, because this n index is size, we have the ability to have more and more complex structures. And as the structures get more complex this way, f is more complex, the energy level increases for the electrons that exist in those energy levels. And of course, electrons that are farther away from the nucleus generally have more energy levels. So we look at the quantized nature of the atom and its arrangement of electrons in these unique shapes. As the atoms, the orbitals get bigger, they have the ability to have more complex shapes. But we see a rule. As the n number increases, so does the number of what? Possible orbitals. That's my L number. So let's take a look at these shapes before we go on to the second and third type of quantum numbers. I'm using still images from the Orbitron website, a great website that shows you these three-dimensional wave functions that electrons exist in. So this is a 1s orbital. Okay, it's a pretty small circular orbital. So if we go here, here are the 2p orbitals. Now notice 2p can't happen until p orbitals can't happen until you have what? You're in the second energy level. When n equals 2, then you can have the L equals 0 and L equals 1. Only that has occurred. So the principal quantum number, n, index of size, tells you how many different types of shapes you have. Now don't get crazy here. These are p orbitals, and there's 3 of them, and I'll talk about why there's 3 different types of them, but this is a type. Okay, we'll talk about them. This is the next number. But look, this is the dumbbell shape. And these, of course, hey, the 2s would be about this same size here. Okay, the 2p is higher energy than the 2s because of the restrictive size, and there's more of them farther away. I'll talk more about that another day. So let's move on here. Here is where we have the 3D orbitals. Now these look kind of crazy shaped, and why? Well, these have what? Unlike p orbitals, who have one distinct preferred axes, okay, d orbitals have 2 distinct axes. That's why L equals 2 here. So if I was to write this, okay, right here, what we have is L azimuthal number equals 2 here. All right, and there's two preferred axes. And that, again, that only occurs when n equals what? You said it, n equals 3, because of the 0 to n minus 1 rule. So the d orbitals only show up in the third energy level, just like the p's start in the second. Okay, let's go on a little even more crazier. Let's look at f's. Now f's have an even crazier shape. Now f orbitals only occur when n equals what? When n equals 4. They first start up in the fourth principal energy level. They can't occur in the first. Energy levels are quantized, and you can't have this complex shape. But f orbitals are when the L equals 3. There are 3 preferred axes for these types of shapes that are very complex and tough to draw. And we actually have G's, okay, which, again, G orbitals occur in excited states. G orbitals, can you guess where they would occur? Okay, well, n must equal 5, okay, for this to occur. All right, and these would have n equals, L would have to equal 4. These have 4 preferred axes, and it goes on. So these are the three-dimensional, and I want to make sure you understand each one of these shapes represents an orbital. An orbital is where 2 electrons can exist. Now, if you notice something, an S only has one form of itself. A P has 3, okay? A D has 5 different types of the same orbital. F's have 7, okay? And that's our next quantum number. Remember, we index electrons based upon their size, and now their type is the L number, and the next one is m sub L. That's the magnetic quantum number. Now, you can guess what that does. That tells you what different type. Okay, now, what is the m sub L number? That doesn't index a type of preferred axes. What that indexes, okay, that m sub L, it basically tells you how many orientations in space they can have. Since the p orbital has one preferred axis, it can exist in the z, the x, or the y plane. And so there are 3 different p orbitals. Remember, an orbital is a pair of electrons. Therefore, the p can exist what? As 6 total electrons. So the p sublevel, we talk about a sublevel, these are all the p's, and 6 electrons can exist in that p sublevel. Okay, but only 2 electrons are ever held in each orbital. Why does p have 3 different? Why s has 1? Why does d have 5 different d orbitals? Hey, the m sub L rule helps us do that. Let's go find that out. So the m sub L, called the magnetic quantum number, and don't forget that, remember, these are numbers from the Schrodinger equation that depend on each other. So we know that n can be any number 1 through 7 and affinity. We know that L is 0 to n minus 1. M sub L's rule, okay, is negative L to positive L. And what the magnetic quantum number tells me is how many of the same type of orbitals. So it tells me that how many, okay, of the different versions of the same type. Okay, we notice S only had one type of orbital. We saw in the pictures that P has equal to 3. We saw that D's have 5 different versions of the same orbital that are arranged differently in space. The magnetic quantum number, okay, indexes how many different orientations in space this type of orbital shape can have. And the F, we're going to learn, has 7. Okay, now you don't have to memorize them, but let's look at the rule. Let's look at S. When S is equal to 0, 0 to positive 0 is just 0. So there's just 0 of the m sub L. The m sub L is equal to 0, which means how many values we count here. And we count just 1. Now, if we do the p orbital, when the L equals 1, put the rule in, negative 1, okay, to positive 1. And we have to go through the 0, okay, to do that. All right, so We got to count them. So if you go -1 to +1 through 0, count how many values we have. We have 1, 2, and 3. So we have a total of 3 orbitals. That's how we do that. Now, when D, we know L equals what? L is equal to what? 2. So we put the rule in, -2 through 0 to +2. Well, it has to go through -1, 0, +1. Count how many values we have here. 1, 2, 3, 4, and 5. And that tells me there are 5 different orientations in space of the same preferred axes or the same shape. There are 5 different versions, okay? And of course, F, I mean, I don't want to F around here, but if I F, okay, that is L equals, of course, 3. Okay, that starts in the 4th energy level. And here, let's do it, -3, -2, -1 through 0, +1, +2, +3. And if you count 1, 2, 3, 4, 5, 6, there are 7 different values here, and that gives us 7 different orbitals. Okay, so that's important. The magnetic quantum number tells me something about the how many orientations of space of the same one. I know it's getting confusing, but stay with me. So what do we know? Well, each orbital holds a pair. Because of the magnetic quantum number, there's only one version of S, just one sphere. And guess what? It only holds what? 2 electrons. Okay, all S's hold only 2 electrons. In fact, every single orbital holds an electron. P orbitals, based on the magnetic quantum number, have 3 different versions. So they get 3 p orbitals. And if I was to draw them, we have one dumbbell in, let's say, the y plane, one dumbbell in the x plane, and one coming at you hard to draw in the z plane. There's 3 of them, 3 orientations in space. But because each one of these holds 2 electrons, and there are 3 orbitals for the p, 3 times 2, there are 6 electrons held in p orbitals. Okay, now that means always they have 6. Even the p orbitals from the 3rd energy level hold 6, and from the 4th energy level hold 6. P's are the same. What's different from an n equals 4 to 3 is just the size. Now D holds 5 different orbitals, but guess what? Each one holds 2 electrons, no matter what. So that'd be 10 electrons are held for the D. 10 electrons are held for the D. And the F, which has 7 different orientations or 7 different orbitals, each holding 2 electrons, has a total of 14 electrons are held. So party people, and people that want to go to the party, we can figure out how many electrons are held in each principal energy level. The first principal energy level, n equals 1, only has an S, which means it only has a maximum of what? 2 electrons in the first energy level. In the second energy level, we only have 2 plus 6 because of the S and P only, a total of 8 electrons. Ooh, the octet rule. Okay, the third principal energy level holds a maximum of 2 plus 6 plus 10. 18 electrons are held maximally in the third principal. And of course, 2 plus 6 plus 10 plus the 14, because the F starts the 4th principal energy level, you get what? You get the 36 electrons held maximally. So this is telling us, based on the quantum numbers and the restrictive properties, how many electrons can exist and what type of orbitals they exist in. Pretty cool stuff. We're almost done. So an s orbital, no matter if it's a 1s, 2s, 3s, of course, it's getting bigger, would only hold 2 electrons. There's only one type of spherical orbital that occurs for the 1s or the 2s or the 3s. There's only one type and 2 electrons. So 2 electrons are in the sublevel s. Now, if you've got p orbitals, whether 2p, 3p, you have 3 different, because the magnetic quantum number, okay, if L is equal to 2, you're going to have what? 0, I'm sorry, -1 through 0 to +1, 3 different possible shapes. And because each of these is an orbital that holds 2 electrons, guess what? You get 6 electrons in your p. All right, and look at your what? Look at your D's, because there's what? L equals what? 2 here, 2 preferred axes. And when you do your M sub L number, which is -1 through 0 to +1, you're going to get -2, -1, 0, +1, +2, 5 different orbitals, okay, and holding a maximum of 10 electrons in the d. And of course, if you've got L equals 3, which occurs first in the n equals 4 principal energy level, okay, you have -2, -1, I'm sorry, -2, -1, 0, okay, +1, +2, and that would work if it's a d orbital. So let's do it for an f orbital. L equals 3 for f's. I'm sorry. -3, -2, -1, 0. Okay. Uh, +1, +2, +3. So the m sub L tells us how many orbitals. And because each orbital holds a pair of electrons, it actually tells us how many total electrons exist in the f sublevel. When I say f sublevel, which is an arrangement of electrons in a principal energy level, I'm including all the possible orbitals. When I see the s sublevel, I'm talking about just a singular orbital because s only holds one. So we're left with the last quantum number. So let's go to it. The last quantum number is m. Okay, the last quantum number is m sub s. Okay, this is the magnetic spin. Now, there's a lot of controversy what spin is, and people just don't know. We know it exists, but we don't know exactly how to explain it. So the spin of electron either goes in one direction or the other, and then that creates an opposite magnetic field. And we've seen this experimentally. Okay, any case, it's the last quantum number. It's not one that came out of the Schrodinger equation, but much later we saw that every electron must have a unique energy level. So the magnetic spin, remember we have the n number quantized by size, has the integers 0 through 7, basically. We have the angular momentum, which is what? Very simply, 0 to n minus 1. That tells us the type of orbital indexed by what? Indexed by preferred axes. 0, of course, is spherical, 1 is a dumbbell. Then we have m sub L, and this tells us essentially how many different versions of the same type, or in many ways, how many orbitals of each type. Okay. How many pairs do we have? Okay, and of course, that is going to be -L through 0 to +L. Okay, and you count how many possible values you get in that number from the L. And of course, that tells you how many. S has 1, P has 3, okay, D has 5 as we just saw. And then we have, and that looks like an M sub L, but now we have M sub S. And this is the spin. And this tells us how the electron sort of behaves inside an orbital, a region. Remember, one of these orbital types, these sublevel types, okay, holds 2 electrons. Okay, so this tells us the spin. And the spin, essentially, you get either a +1/2 or a -1/2. That's the notation. And the way to try to understand it, if I have an orbital, it's an S, it's spherical, L equals 0 and N equals 1. Okay, if I've got it, I know electrons aren't particles, but if I've got an electron here and I've got an electron here, if this is going to move this way, won't it make the electron move opposite? I know it's an analogy and I'm really kind of breaking physics by saying it as particles, but we don't know exactly, but we do know the electrons move differently in orbitals. And what we do is when we do orbital notation that we'll see, we tend to show an arrow going up for one type of spin, an arrow going down. So we call those spins 1/2, or +1/2 or -1/2, and they're based upon how electrons have a certain kind of motion, okay? And their different spins create opposite magnetic fields. So that does happen. We just don't quite wrap our heads around it. So it's important to realize that these quantum numbers help us index size to type to how many, and eventually what the electrons look like. And so all these kind of rules help shape the arrangement of the atom. As we said, the first energy level holds 2, the second energy level holds 8, and so forth. But let's talk about how I'd answer a question, because the whole point of these questions is to come up with the quantum numbers. So let's say I have helium, okay? Helium. And helium has atomic mass of 4, atomic number 2. The atom of helium has 2 electrons, okay? And we would draw a box to show it fills 1, because helium's in the first row, we would write the configuration of helium 1s2. That means in the first energy level, remember this 1 is the n number, and because the first energy level only can hold an s, okay, it has 2 electrons that fill the s. And we show the boxes going up and down to show the spin. So this would be the orbital notation, okay, and this would be the electron configuration. Remember, this 1 is n equals 1. And remember, electrons in the first energy level only hold 2 electrons because they only have an s. Let's prove that. So I want to draw all the quantum numbers for each of these electrons. So for this electron, here's what I would do. I would say n equals 1. That's the first quantum number. Now, once I know n equals 1, what does L equal? Well, L equals what? L equals, well, what's the rule? It's 0 to n minus 1. So 0 to n minus 1, well, if n equals 1, it's 0 to 0. I just have a 0, which we know better as an s orbital. What's m sub L? Okay, this tells me how many different types. Well, let's go negative L, 0 through positive L. Well, you put a 0 in, it's just going to be 0, and you count one of them, and there's just, okay, a 0 value, which means there's just one of them and there's one orbital. And the first one will just do m of s to equal positive 1/2. What does that mean? Okay, we're just saying that is going to be the spin up. And you could have started with spin down. It doesn't matter. But these are the 4 quantum numbers. Now, what would be the quantum numbers for this second electron? Well, it's still in the first energy level. Remember, helium is in the first energy level. Okay, so n is equal to 1. Remember, helium's in the first row. L is still 0 when you plug them in. M sub L is still going to be 0 when you plug that in. That means there's only one unit value here. There's only one orbital. But the m sub s, the spin, is going to be plus 1/2. Okay, and I've just written the 4 quantum numbers for this second electron here. Every electron has a unique set of quantum numbers. That's the Pauli exclusion principle. That makes every electron have a unique energy, and it makes atoms be unique because not really the protons in terms of energy, it's the electrons. So those are the 4 quantum numbers. And again, helium has 2 electrons. Because there's only what? A 1s for the first 2 electrons, if you want to write them this way, we say in the first energy level, there's an s orbital with 2 electrons, and we are building something called electron configurations. Okay, so that's how you do it. You follow your rules. Okay, now if I do another example, okay, let's do lithium. Okay, so lithium, mass of 7, 7 up, atomic number 3. If we go to the periodic table, lithium here exists in the second principle or period. Okay, atomic number 3. You say atom, I say neutral. Atomic number 3 means it has three electrons. The first 2 electrons have to fill the lowest energy level. It's called the Aufbau principle. So we already know the quantum numbers of lithium for the first 2. It's the same as helium. Notice helium's in the first row. 2 electrons fill the first row. Okay, so lithium has 3 electrons equal to the 3 protons that make it an atom, which is neutral. So what would be its quantum numbers for its 3 electrons? Well, we already defined the first 2 electrons that are filled closest when n equals 1. They'd be the exact same numbers, okay, for helium. But then we have an additional electron that's now in the second row, okay? And so if we look at configurations, we would say 1s2 for these 2 electrons, and now we've got electrons in the second row, and this would be 2s1. Okay, and this would be something called the s block. Notice there's 2 electrons in the s block, total 1 orbital. This right here is the p block. Notice how many columns? 1, 2, 3, 4, 5, 6. There's 6 electrons in the p block. Hey, there's 3 different types. This right here is the d block. If you count the rows, you'll count 10 electrons. Okay, divide by 2 for how many different orbitals? 5 different orbitals. M sub L is 5 units. And down here is the F, and that's right, you'd count 14 for the 7 orbitals there. So let's go back. So for lithium, the configuration is 1s2. The first 2 electrons fill the first energy level, and we say it's filled. But now it's got a third electron. Where does that go? Well, it has to fill the second energy level. n equals 2. Okay? And we start with another s, and that'd be 2s1. Now, if I do boxes for orbital notation, the first two boxes, like I just showed you for helium, would look the same. This would be a 1s orbital. Now, it's not a box, but we show electrons. And that fills. You can't have 3 electrons in the second energy level. Why? Because when n equals 1, L is only equal to 0, which is just one type of orbital, and that one type of orbital, m sub L, by our rules, only gives us one unit, a 0, so there's only one of those orbitals, and each electron has opposite spins, so 2 electrons fill the first. So the third electron, the exponents of electrons, would have to go when n equals what? 2. This now becomes what? 0 and 1, right? So what's the rule for the m sub L? The rule for m sub L is, for L is 0 to n minus 1. So 0 to n minus 1 gives me a 0 and 1. But we have to fill the lower energy level S first. And that tells me that a P eventually is going to come into play once we fill the S. Okay? So what would be the quantum numbers? For lithium, the first quantum number, 2, would look exactly the same as helium, because its first 2 electrons would have to fill the 1s2. Electrons fill low energy positions first, and then they're forced to go outward. Again, that's the Aufbau. So the electrons here would be n equals 2 for this electron in this box. Okay? L, we know, can be 0 and 1, but we're going to fill the S first. S is of lower energy. It's a more simple structure. So that would be 0. That means what? M sub L is 0. Okay? And then the M of S spin will go positive 1/2. Notice these 4 numbers are not the same as the first 2 numbers. Every different electron has a unique set of 4 quantum numbers. And we write the configuration of lithium 1s2, 2s1. How many total electrons? 3. First 2 electrons fill the first energy level. Bohr would call this a shell. The third electron starts the second. And if we go back to the periodic table, okay, beryllium would be 1s2, 2s2. And this is the p block. Hey, we just filled. Beryllium is 1s2, 2s2, and 2 electrons fill the s. We know there's only one s, and there's an L equals 0 and 1. We start filling the p. This would be 2p1, 2p2, 2p3, 2p4, 2p5, and 2p6. All right, as far as I want to go. Please try the form, and good luck.